大変長らくお待たせいたしました。ただいまより NVIDIA HPC Solutions Development Stan Posey より GPU Progress of CAE Applications について講演を行います。Ladies and gentlemen, please welcome Mr. Stan Posey.
Thank you for that introduction. Good afternoon. I'm going to take a few moments to share with you some of the progress NVIDIA has been making with CAE applications. I've been involved with this effort now for the past 4 years at the company. To start with, I'll just give an overview on the GPU Parallel CAE as it exists today. Most notably, there's been very strong investments by ISVs, and I'll give some examples of that as we go. Most of the adoption has been led by implicit finite element analysis, but also the electromagnetics has been very strong, and then followed by CFD. And you'll hear more about that if you are here for the next session, which is very detailed about our CFD progress. GPU computing for the ISVs has been implemented in a way that helps to preserve the costly MPI investment. You'll hear more about that. And as we see now, there's been several customers who have put into practice GPUs for leading applications. And that's been led primarily by the automotive industry, but also the electronics, and now aerospace is beginning to adopt this. And GPU acceleration has also contributed to the areas of emerging CAE, if you will. New ISV developments in particle-based CFD, for example. We'll see a few examples. And then, in particular, electromagnetics has been growing very rapidly with a lot of the sensors that exist in many of the designs. So, as a company, NVIDIA understands CAE very well because we use this technology in design of our own products. And this runs the full range of disciplines from structures to fluid mechanics to electromagnetics. A lot of our simulation is based on Ansys products, as you see in these examples. But there's a wide variety of applications we use in our product design. And if you're familiar with some of the large-scale systems that have been deployed in the top 500, I wouldn't say that CAE exists at that scale. But for those of you who are familiar with workstations, the Maximus Technology in particular, the same GPUs that exist in that technology are also used in some of the very large systems such as the Titan. The Titan does have a few applications in the area of research CAE, such as, in this case, turbulent combustion. But NVIDIA has the same technology and is able to leverage a lot of its HPC R&D by maintaining this kind of scale at both ends of the hardware requirements. Now, the Maximus technology itself, if you haven't been introduced to that, I'll give just a brief review. It's a technology whereby you've always had a Quadro in your workstation, and now you add a computational GPU, which we call Tesla. When you present a task to the workstation, the Maximus technology knows whether to send that task to the computational GPU or the graphics GPU. This is all done automatically from a single unified driver, which really simplifies the implementation for our users. And there's been various areas of success. Delphi is an automotive supplier based in the United States. They also have business here in Japan. They've now standardized on Maximus technology for production level CAE. And here's an example of some Ansys models, 3 different Ansys models, and the kinds of speedups they were able to achieve. On average, about 50% speed up by deploying the Maximus technology with Ansys Mechanical. And we're not only looking at how do we satisfy solutions at the ISV level, but looking industry-wide. Let's take an industry that's very important to the company, in this case automotive, and ensure that we have the entire requirements completed for what's needed in an automotive CAE environment. Here's a list that shows select applications in the area of structural mechanics and fluid dynamics, the typical CAE software that's used in these applications. There's a few standards that have been emerging over the years. And then the status as it exists today. So everything available today is in the red color. And you can see we're doing a pretty good job of satisfying most of the requirements of automotive and have more work to do, but we're making good progress. But on the whole, I would say that every ISV, and especially the really large ones in the industry, have some product or evaluation ongoing with GPUs. This shows you a list of what's available today very briefly, and I'm going to go into more detail. The products that will be available during 2013, and then various product evaluation and research evaluation that's ongoing throughout the industry. Again, the focus is on all three domains: structural mechanics, fluid dynamics, electromagnetics. And you'll see as we go through this some of the achievements that have been available with GPUs. Now, just a summary on the success that the industry has seen so far. Again, every primary ISV has some product or project ongoing. The four largest ISVs all have primary products on GPUs today. That would be Ansys, SIMULIA, MSC Software, and Altair. In that order, they comprise the largest ISVs that make up this industry. We also have now the top 4 of 5 applications. And by that I mean those applications that seem to be used more in industry than others and drive most of the market share, if you will. And then there are several ISVs who have begun their company with a strategy based on GPUs as an HPC competitive advantage. One of those is based here in Japan, Prometech, with their ParticleWorks software. There's a few of these new companies developing, mostly outside of the US, and you'll hear more about them as they grow and develop their business. And then finally, the availability of CEM software has been growing rapidly. I'd say that's been the highest growth that we've seen on GPUs in the 3 disciplines that we've mentioned. And I will make a special mention that Ansys will release its first major product, HFSS, which is a large application in this market, during end of 2013. So, how did NVIDIA get to this point? You know, we had to start somewhere, and we set our priorities based on a few characteristics that exist in the software, trying to understand where's the fit, where should we begin. And there's 2 attributes for software that typically determine what you can expect for performance. That tends to be the time integration scheme that you see on the vertical axis, whether that be explicit or implicit, and then the mesh type across the horizontal. And just to give you some examples, down here in the corner where you see direct solvers, 75% of the time is typically spent in matrix factorization. That's a double precision matrix multiply, very good fit for a GPU. That naturally became our top priority and our #1 focus, given that you have that heavy amount of computation in the factorization. So everything implicit structural mechanics became our top priority, #1, the list that you see there. The next area was iterative solvers. These have less of a hotspot, 50% more or less versus 75%, but you can still take that amount of operations and accelerate it with a relatively small amount of work. So the applications that exist in structural mechanics for iterative solvers along with CFD became the #2, #3 areas of focus, the priority. Now the 4th area, which would be explicit schemes based on either structured grid or unstructured grid, but I'm going to refer mostly to finite element, mainly the codes used for crash worthiness. They don't have a hotspot. They don't have a solver. They do operations on a stencil. They don't have the ability to move to a GPU very quickly. They depend on compiler technology, and that's where we stand at the moment and why you haven't seen a lot of the explicit software available yet. It will evolve as the compiler evolves. So what is it the ISVs are doing then? So we're going to concentrate now on the implicit, because that's where the concentration of all the work has been. There really hasn't been any progress in explicit. And here you see a typical schematic of an application starts on a CPU and finishes on a CPU, just like you've always understood and experienced. But the ISVs have implemented a part of the execution profile. In this case, I'm showing 40 to 75%. That represents that implicit hotspot. Those matrix operations get pushed to the GPU because they're such a good fit for those kinds of operations. And the ISVs have deployed different strategies for that using CUDA, GPU libraries, cuBLAS is an example, or OpenACC directives. Various ways that ISVs can achieve their matrix operations being moved to the GPU. But this is really all transparent to the user. This schematic shows here where if you've got a GPU connected to a CPU, all you have to do as a user is just tell the software that a GPU exists. It's just a flag, on or off, I have a GPU. In every ISV, this is the case. The job still starts on the CPU, ends on the CPU, just like you've always seen. And what happens in between is the GPU recognizes when matrix operations should be moved to the GPU and will take care of that for you. The ISV application is automatic in that way. So what was the motivation? You know, I look at the history of microprocessors over the year, and none of them have been successful without the presence of ISV applications. So ISV applications really validate your success in your product. And we've had the four largest, again, making strong investments in GPU computing. What was the motivation for this? Well, I think they really play into the key trends. GPUs play into the key HPC technology trends that are central today. Here's four that I would like to share with you. Everyone's going after higher fidelity. This is true in the CPU world, the GPU world, but in the case of GPUs, we can permit that higher fidelity within your CPU time that you're accustomed to. Meaning within that same turnaround time you have today, you can do a much higher resolution model. Maybe you'd like to do a parameter sensitivity study where you would actually add the number of jobs, still keeping your overall simulation time that you were accustomed to with CPUs the same, just doing more work within that same amount of time. And typically at lower cost. We'll investigate some of that. But GPUs are also a method to look at some of the advanced techniques that are coming, areas that are maybe considered not practical today, transient simulation, for example. These will all come in a much easier way for us with the use of GPUs. The use of finite elements with solids versus shells. Shells are typically 2D. Solids have more work, but there's usually not any additional cost on the GPU for such elements. So these kinds of thinking can change when you have this technology available. And then the growth in ISV software budgets. The GPU tends to provide you more use of the software for the same budget. It's becoming very important as ISV software investments becoming very large. In fact, if you go to a place like Detroit and the automotive industry, what they share is that over the past 20 years, they've seen people and software become the area where the cost is really focused, not the hardware. Hardware is getting very inexpensive. And for every dollar they spend on hardware today, they spend $4 on ISV software. This is a rough estimate based on the three in Detroit area. And so the emphasis becomes this last point here where there's increasing importance on not saving money on hardware, but implementing hardware that helps you manage the cost of people and software. Very important now in the industry. So I'll talk a little about a few of our collaborations. The first with Ansys. Ansys has invested in all three of their major discipline thrust, structural mechanics, fluid mechanics, and electromagnetics. They've been committed to GPUs going back to December 2010 with their first release. I won't go into the detail of each release, but there's been a progression of features that have gotten Ansys Mechanical to the same level of what you would expect in CPU computing, meaning that there's no limitations now to the use of mechanical on GPUs. We're now starting with Ansys Fluent. This year, in November, December 2013, you'll see the first release of Ansys Fluent on GPUs. And I'll show you a little bit of information on that. And I mentioned earlier this release of the first HFSS. It'll be a transient versus frequency mode, but that will come in Ansys 15 also. Again, scheduled for November, December at the end of this year. So just to give you a very quick snapshot of what's possible with Ansys Mechanical if you haven't seen, we've got two configurations here, a Westmere and a Sandy Bridge-based workstation or server. You've got 12 cores on one system, 16 on the other. I'm showing you the result of using 8 cores. This will be akin to turning on an HPC pack in Ansys. So 8 cores on each of these systems. You can see some cores are idle in the configuration. But if you were to run in this kind of setup, you would see, for this model, 2 million degrees of freedom, turbine geometry. You would see 164 jobs per day on the Westmere system, 210 jobs per day on the Sandy Bridge system. So higher is better. So that's the kind of performance throughput you can get with a CPU. If you add a GPU to each of those configurations, one GPU, Ansys now allows you to add multiple GPUs. If you just go with one GPU, you'll boost these each by about a factor of 2. So you'll go from 164 to 341 jobs per day, something similar, 395 jobs per day with the Sandy Bridge. So that gives you some indication of what's possible today in applying this technology. Now, Ansys has done a number of benchmarks themselves. They've published a lot of results. I'm referencing here a talk from Jeff Bysham at Ansys in their headquarters, who does their primary HPC development. He gave a talk at the Ansys Automotive Simulation Conference in 2012. You can go and download this and see performance that he shows for an engine block, 6.5 million degrees of freedom on 8 cores versus 8 cores in a CPU or a GPU. And then in the same presentation, he talks about some of the multi-GPU results that are available. In this case, he applied 16 cores and 4 GPUs for this case from the heavy industry. So a lot of good work coming out of both organizations to show the capability. So let's talk now about what SIMULIA is doing, the second largest ISV in this market. Similar to Ansys, they've had a progression over time. They started in June 2011 with their first release, Abacus 6.11. Over time have progressed to their most recent announcement of Abacus 6.13. And they're, without going into a lot of detail, they've completed all the requirements to get to full feature. So today, Abacus is multi-GPU, all solution types, both for static and dynamic, and have practically removed any limitation that might have existed when they started in this process. And also have implemented some very nice Kepler optimization. This gives you an example from a customer of NVIDIA's, Rolls-Royce, who now has Abacus in production on GPUs. And you can see in the first result, 8 cores, and then next to it, 8 cores adding 1 GPU. There they saw a speed up of 2.42 being applied to a 4.7 million degree of freedom model. Very nice speed up for what's available. And this progresses as you go out to adding more cores and more GPUs on a single node. So for a fully populated node at this end, 16 cores versus 16 cores plus 2 GPUs, that speed up was greater than 2 at 2.11. They also demonstrated for this same model what could happen on multiple servers. Abacus has a nice distributed memory parallel implementation, and you're seeing the results from 2 servers to 3 servers to 4 servers. And as you go out, they're adding more GPUs to the existing number of cores, 24 cores, 36, 48. And you can see when you get out to 4 servers with 48 cores, and then add 8 GPUs to that 48 cores, you're seeing a speed up of 1.8x. Very nice implementation that allows you to scale to a large number of servers for model sizes that are not that large for industry. A third example, MSC Software, roughly the 3rd largest ISV in the industry. They just made an announcement of the release on 2013 and are also working in a way to remove any limitations that may have existed before. I won't get into a lot of the details, but the largest impact you would have in your work with MSC Nastran would be in the area of Solution 103, 108. These represent static simulations. Solution 103 is dynamic response using modal frequency, NVH, if you will. And then Solution 111 is another approach to modal frequency response for NVH. Depending on your solution sequence, the performance will vary. You can see that they've now implemented, though, in a similar way, running on multiple GPUs and allowing you the full range of capability with their latest release. So here's one quick example from the automotive industry. This shows a Solution 101, which would be linear statics, and then a Solution 103, which would be normal modes extraction. And you can see the speedups, in, as I mentioned earlier, are much stronger in linear statics currently than they would be for an NVH type simulation. But over one core, you're looking at 6x speedup, and over one core, 2.8x. So speedup's very similar to what's been achieved in some of the other applications that I showed earlier. Now, for a specific NVH problem in particular, this is where you would apply direct frequency response to NVH. There you can see speedups that can go as high as 11x when you apply 8 cores and 2 GPUs over what's possible on a single core. A very dramatic speedup for a model size that's not that large in the industry, 710,000 degrees of freedom, with representing about 4 million, nodes representing about 4 million elements, and looking at 100 frequency increments, which would be very close to an industry scale model. Final example from Altair Engineering, roughly the number 4 ISV in the market. They've got a nice implementation of an iterative solver in Radios based on a PCG implementation. And this shows what's possible with theirs in an automotive example of pressure load on a hood, where they show using 2 GPUs on a single node, they're at a level of 7 times faster. This is being applied against a single socket Westmere for that speed up. Applying GPUs, 4 GPUs on 2 nodes gets them to a speed up of 13x for this particular model. Now, this is an iterative solver. The solvers I showed earlier were all direct. They have different behaviors, different speed up characteristics. Every model presents a different situation. So it's really a matter of understanding what's been shown in these benchmarks, but then trying to apply that to your own application and your own interest in the cases you're looking at. So just as a summary, we see that GPUs have provided a significant speed up. Now, I'll make a couple of comments that even though all limitations have been removed, if your model size is less than 500,000 degrees of freedom, you may or may not see benefit from GPU. There's perhaps not enough work. It's one idea I will mention. Another idea is that if you're using shell elements, there may not be enough work compared to using solid elements. So while these limitations don't exist, you just may not see enough of an acceleration with these kinds of features in your model. So again, there are things to think about. But roughly, when we see that an application or a particular case becomes solver intensive, again, where I have most of the time spent in the solver, GPU can do very well. And apply in those areas I mentioned about improving product quality, fidelity of the modeling, and shortening product engineering cycles if you want, with faster turnaround. We also see that some simulations that were recently considered impractical have now become possible. So in finite element analysis, it means larger degrees of freedom in your model, as I mentioned, more complex material behavior if you want, fluid structure interaction. All these things become more practical when you have speed-ups that exceed what's possible with CPUs today. For CFD, it means looking at some transients that I mentioned earlier. Unsteady Reynolds average Navier-Stokes, LES simulations, these kinds of simulations that don't appear practical in time and cost today are something we can now look at effectively. And then parameter optimization from a large increase in the number of jobs. We see that the throughput available with GPUs can get you closer to more parameter sensitivities in your study, and something that all organizations are trying to achieve at this point in our progression in the industry. So that concludes my talk. Thank you for your attention, and we do have time for questions if you like. Thank you. I see a question in the back. I don't know if there's a microphone available. One of the organizers. Thank you.
2点、吉田と言います。2点質問あります。1点目は27ページの拡大しているところの説明をお願いします。
Please. Can you repeat, please? Oh.
そこの中央の拡大している絵の説明をお願いします。
Oh, yes. Okay. Thank you. So what I'm showing is the geometry that exists for this metal formed hood. But the blow-up that you see, and I'm sorry if it's not that visible, actually shows the finite element mesh discretization for that particular model. You have a total of 2.2 million degrees of freedom. So you're looking at the granularity of that mesh in this cutout here.
はい、わかりました。あともう一点、ノンリニア非線形問題の典型的な問題として、コンタクトのインプリシットインテグレーション、これ将来、実現可能かどうか教えてください。
Okay, so what I believe your question is about is related to an explicit application that has contacts that use an explicit scheme. Is that correct?
インプリシットのコンタクト。
Okay, okay. So the implicit contacts haven't been addressed yet. So if the application is implicit or explicit, the contact is usually always implicit for both. Okay. The contacts haven't been investigated yet because all of the emphasis for now has been in the linear solvers. Everything I showed you today was practically linear solvers. I agree there's opportunity in contacts, but it's like any tuning effort where you start with where you get the most return on investment. And so I think all of that will come. Contacts will come, but today there's not been a lot of work in that area. But that'll be very important when we get to the explicit application because they can spend a very large amount of the total time in the contact. So thank you for asking that question. But I agree there's opportunity.
はい、どうもありがとうございます。
Other question, please. Yes.
ちょっと ISV の話じゃないのでご存知だったらちょっとお話を聞きたいんですけども、今のお話聞きますと直接法を GPU に載せる研究というのはかなりISV の中では盛んに行われているようなんですが、そういったその直接法のソルバー GPU 上のですね直接法のソルバーっていうのが単独でこう商用になっているものがあるのかとか、もしくはその公開のその直接法のソルバーが何か研究されているような動きがあるのか、その辺の動きをご存知だったらちょっと教えていただきたいんです
けど。Thank you for that question. Question related to direct solvers and whether there were, say, open source implementations available. First of all, I'd like to comment that for the ISVs in the area of commercial direct solvers, practically all deploy some form of what's called as a multi-frontal sparse solver. These are common in the research community. I would say they each have some proprietary implementation of that. But really, the key development that has made them successful is to ensure that they can take advantage of the DGEM operation on the GPU. So DGEMM, which is the Kublas double precision matrix multiply. This is NVIDIA's responsibility to make sure that goes faster with each release of CUDA, each release of GPU architecture. If we can make that fast and the ISVs use that operation, they'll continue to grow their performance with NVIDIA performance. So I would say that's their primary strategy. But as far as research, I'm here throughout this reception this evening. There's a lot of research, and I think things that can be implemented. I would point you to UC Berkeley, Jim Dimmel, some of the work they're doing. There's been work out of Bob Lucas. There's quite a bit available, and I believe, I don't know this for certain, but I believe the ISVs implemented their solvers based on some of the early research. But again, all are slightly different. But if you focus on the kernel and get the most out of that, you can benefit with each succession of release, which again is the DGEM operation, which is very critical to the direct solver. Thank you for that question. I'd like to mention too that I didn't spend a lot of time to focus on the CFD. I was asked to do that in the next session. So if you're interested there, we're going to review Ansys Fluent and Openfoam. Openfoam is an open source CFD in the market. And you can see some of the GPU developments that have been implemented for CFD. This has been really more of a focus on overall CAE and then some detail on structural mechanics in particular. Okay. Thank you all for attending my talk.
Thank you very much, Mr. Posey. 以上をもちまして本セッションを終了とさせていただきます。ご利用いただきました同時通訳レシーバーはお席に置いたままでご退出ください。また本日お配りいたしましたアンケートにもご協力いただきますようお願い申し上げます。この後およそ15分間の休憩を挟みまして17時40分より NVIDIA テクノロジーセッションセッション6 GPU Acceleration of Applied CFD のセッションを開演いたします。開演まで今しばらくお待ちください。